Yeah, boy, too bad for the guy that has to follow Tom Daly's presentation. Oh, right, that's me. Damn it. Anyway, my name's Joe Kottke. I'm the VP of Engineering at BrightTag. It's a tag management startup in Chicago, and I'll talk about how to scale in the cloud cost effectively while still maintaining performance and maintaining your SLA. My talk is a little bit sort of policy. You know, we're talking about SLA and cost, which is kind of sometimes a little boring. But for the most part, I'll start out with covering some of the details around SLA and just concepts, and then we'll get into some more technical stuff. So roll with me on this, and it gets more fun and techy and nerdy near the end. So like I said, I'm the VP of Engineering and Infrastructure at BrightTag. We are a tag management service and a data service manager, I guess. We help site owners optimize the delivery of their ad server tags, marketing tags, retargeting tags, impression beacons, that sort of thing on their websites. My elevator pitch is not that strong. So if you want to talk about it more, I'd be happy to tell you all about it. It's actually pretty cool stuff. So where have I come from? I started work in the tech field about 20 years ago. I helped to start a company called Geek Squad in Minneapolis, and I learned my love of Unix and Linux there. I moved on to the advertising corporate IT space with a company called Interpublic Group, and I learned distributed systems, solving just sort of neat little dumb problems for interior agencies to communicate with their clients, and really got into writing distributed applications there. I then moved to a company called FeedBurner in Chicago, which was a RSS management application and proxy, and got my first taste of big systems, big data, high performance distributed systems, and then that company was acquired by Google in 2007, where I got to learn a lot of the fun distributed system secrets that we've applied at BrightTag today. So SLA and cost. You know, we all know what SLA is, I think. Your service level agreements. The neat thing about it is you have to define these things to know if you're successful. So you obviously have to define your SLA for your clients, for your customers, even for your own internal groups, people within your organization. And you know, it can be the number of nines, your 4 nines of uptime, or your performance of your application in the 95th percentile of all responses being under, say, 70 milliseconds. But also then for cost, you want to sort of tie it. I think that you should tie it towards what your company does and how your company makes money. So in the advertising tech space, a lot of things are calculated, or cost is calculated based on cost per 1,000 requests, CPM usually. So you can define your 5 cents per month per request or per conversion, but in our case, we define it based on how cheap can I get our infrastructure while still maintaining a high level of performance in SLA. How cheap can I get it on a per 1,000 response or request basis? And the closer that I can get it to fractions and fractions and fractions of pennies, the better. And we're doing a decent job of that. Before the cloud, I loved hardware. I still love hardware. I love everything from racking machines to building data centers to just even amassing and collecting hardware. I unfortunately still do that at home. But I loved everything about it. You knew how to monitor it. You knew how to trust it. You knew how it would fail, how you would deal with particular failures. And the cloud and in EC2 or Rackspace or wherever, you're effectively being lied to no matter what. So your CPU usage obviously is not really the CPU usage. It's what some fraction of the physical CPUs you get to use and how much of that fraction you're using and how much maybe you're getting squeezed out of it. And all that stuff just sort of terrified me. EC2 came online, I think, in 2006, and we were in the middle of turning FeedBurner into a multi-data center application, serving it out of multiple locations in the US. And it looked interesting, but honestly, it looked really difficult. And to be perfectly honest, it scared me. Like I didn't know a way to wrap my head around it. So I kept on my blissful ignorance of the cloud for as long as I could. And I left Google in 2010 and joined up with Brightag. And my CEO, who was all abuzz about the cloud, which also pissed me off from time to time. Oh, just put it in the cloud. Just, you know, it'll go faster in the cloud, which is just garbage as just a blanket statement. My CEO was on this bandwagon, and I couldn't fault him for it because he didn't want to spend any money whatsoever on hardware. He didn't want to have any capital expenditures. Talk to your nearest financially smart person and ask them why it's, in some cases, better to do operational expenditures versus CapEx. But he didn't want to carry hardware. He wanted to be nimble. He wanted to not carry the burden of depreciating gear, basically. So I took that on as a challenge. And what happened was we had our first working demo, fully working demo within 4 weeks of the company starting. We went out and chased funding with it. We acquired clients with it, and to that end, everything about the cloud was true. We spun up servers, we spun up applications, but we did it like this. A little for loop with a call to the EC2 run command with some crappy shell script that's attached to it, but that's where we started, and it worked for 5, 10 machines just to get something running. But we knew that we had to, in that first month or those first 2 months, we knew that we had to take on a much better design and a much wider sort of perspective on how we would make all of this stuff work and what sort of goals we wanted to achieve in serving out of the cloud. So we kind of came up with a couple of basic design points. And honestly, these aren't necessarily specific to the cloud. They can be applied to they can be applied to physical hardware. They can be applied to any of the cloud infrastructure. They can even be applied to your own internal cloud systems, like if you're running OpenStack. And that's an overall part of our design, was we didn't even necessarily know if we were going to stay in the cloud. So we wanted to have larger goals beyond just including EC2. So we started out by breaking up our application into 2 aspects. Our UI, our management UI, and our serving platform. Given the choice and under duress, obviously we're going to offer a higher SLA, and it's going to be more important to serve our clients' users than it is for us to serve our clients and their ability to see their graphs and see their statistics and see things and manage their configurations within our system. So we broke the application up into 2 separate chunks. And that way we can define different SLAs for different applications. We have a much higher SLA for our serving architecture than we do for our UI. And we also devote a lot more of our money going towards it. Everything is a service-oriented architecture. So everybody familiar with what that is? I would assume in this crowd, yes. We break down all of our, instead of having one big monolithic app, we have a bunch of little interconnected services that all talk to each other. It allows us to scale each layer independently. It allows us to tune performance characteristics at each layer differently. Certain things like if you've got small services that do a lot of rapid small payload communication, you treat that much more differently than a larger application that's doing longer polling or longer held connections with much larger payloads of data. So by breaking up those services, you don't have to apply the same hammer across the board. You don't have to deal with a big monolith, which is scary and confusing. I didn't really even understand this scene in 2001. I thought I did, but I didn't. We want to have a minimal center, so no node, no region, no data center is really of any higher class than the others. So you don't rely on sort of the important one or the configuration is all stored in US East. If all of your systems or all of your regions are equal citizens, then you can route traffic and you can treat them all equally, which just makes maintaining your SLA, maintaining your performance a lot easier. This, of course, implies that it's all multi-data center. I'd sort of use data center and region interchangeably just because I still have a little hard time letting go of that hardware. So everything, the application was designed from the ground up to be multi-data center aware or multi-region aware. And also that it wouldn't, any one particular, like I said, any one particular region wouldn't have to rely on another. We also we didn't want to use any EC2 specific technology. We wanted to be able to take anything that we've applied or learned and actually go back and apply it in rack space or apply it in Linode or apply it even on our own physical hardware or our own private cloud setup. We can take our toys with us. So, but honestly, auto-scale groups are so cool, are so fantastic, and so is the spot market for buying instances. So in those cases, we do use specific EC2 tech, but we also have alternatives that work almost the same way to be used in other environments where you obviously don't have this kind of technology. We also wanted to minimize any cross-data center traffic. So it's, especially if it was something that would be blocking a front-end user request, you don't want to, as your user is connected and has issued a request, you don't want them waiting while you go across the country to retrieve some bit of important data to then come back and deliver that response, and already it's 50 milliseconds too late. And obviously there's some transit costs associated with that. And finally, service close to the user. We heard this in the Dyn presentation. The closer you are physically, your servers or your instances are to the user, the faster it should be. Longer distances equals more latency. So how do we do this? We started out with some general things that we knew we needed to follow, and I'm going to kind of talk about some of the basic tips and how they apply to either your SLA or your performance or your costs a little bit. So starting out, you need, no matter what, you need these things regardless. You need configuration management. Excuse me. You need configuration management. It doesn't matter if it's Puppet or Chef or CF Engine or WarSync, which is some little thing that a friend of mine wrote a long time ago. You need to, when you have a bunch of servers and they're all running different applications, or they're tuned or they're configured for different reasons or for different uses, you still need to configure each one of those uniformly. You never ever want to be in the position of having to configure these things manually. You're always going to break it. You're always going to do it wrong. You're always going to fat finger something somewhere, and you've already got a somewhat unreliable system, meaning EC2 or the cloud or whatever, that's already working against you. You don't want to add your manual steps on top of it to work against you as well. You also need monitoring. Again, it doesn't matter what you use. Nagios, Monet, Moonin, Cacti, Graphite. You need something that will tell you when you're doing things correctly and when you're doing things wrong. Even if your basic entry-level bit of monitoring that you have a brand new application, you don't know how it's going to perform, you don't know, you've done your load testing, you've done your unit testing, your regression tests, but you still don't really know how it's going to perform once it's deployed in production and running. You need these sort of tools, or these basic things to tell you, all right, well, why is the CPU too high? Why is the load too high? Am I using more or less memory? If you also include queries per second or requests per second and latency, those things you might need to instrument your application a little bit to get those. But I would say that these 5 things, this is the bare minimum you want to be monitoring and alerting in your application. If not, you're flying blind. And it'll become, I'll show you in a second why these particular things are important. Also, if you're running a bunch of services, choose your transport ahead of time. And maybe you don't use one common transport across everything, but make sure that the services you're building and the people and the engineers that are writing the code understand why you're making choices about certain transport types. HTTP, we actually use that a lot, even internally, with RESTful services, mostly JSON payloads. It's really easy to load balance. It's really human readable, and you can test it with curl commands, which is, I think, as systems get bigger and faster, obviously you have to move towards maybe a faster binary protocol or switching to UDP or doing all sorts of other things. But the longer that you can keep these services or these kind of things this easily testable and this easily readable, like I would guess almost everybody in the room knows how to mock up their own HTTP request, even with Netcat or with piping it through Telnet or doing something weird like that. That ability to test that that way, just to spot check your services, is critical. You can also go the binary route. Thrift is fantastic for this. It's good for native non-HTTP services, and it's binary, it's fast, it's, what's going on here?
Get a little bit of interference.
Okay. It's binary, it's fast, it supports all sorts of languages. You have to bring your own load balancer. You can't, you usually have to either, unless somebody's written a generic thrift load balancer, that's something I've been considering and been looking for quite some time. Anybody? Damn it. You have to write the intelligence of load balancing into your thrift clients. And this works well. We actually use thrift for a lot of our logging for our stats aggregation through the use of Scribe. And then you have your native transports, Memcache, Redis, RabbitMQ, whatever. If you're going to use these services, you can't necessarily get around these unless you front them with your own service, which then you're adding latency, you're adding a failure point. Why would you necessarily bother? So for the first sort of hot tip that applies to SLA and performance, obviously you need to use load balancers. Or you should use load balancers. This, I would think that everybody's familiar with this in this crowd here. HA Proxy, Varnish, and even Nginx or Apache have basic load balancing semantics in them. HA Proxy is fantastic as a software load balancer, absolutely incredible. Varnish does some really neat things with being both a load balancer and a really interesting caching layer as well. And if you're using, again, this is a good reason to use HTTP as your transport, because you can just throw this in front of a bunch of servers, and you suddenly have a redundant service. Elastic Load Balancer with EC2 is awesome, but it's Amazon-specific stuff. GSLB. So this is the follow-on to just regular load balancing, and again, they talked about it with the Dynect talk right before me. This is global server load balancing. People call it other things, but this is what allows you to have multiple data centers that don't talk to each other, that don't care about each other, that don't do anything but serve up your requests, but every data center serves up the same requests in the same fashion. If you can route your users to their closest data center, you will see a huge performance increase. So if you're building something, if you're building something EC2, keep in mind that it's really easy to spin up instances in East just as easy as it is to spin them up in West. And if you can include that in your design, it will pay off quite a bit as you continue to grow. So GSLB can take the form of DNS-based. I actually use Dynect service, and I absolutely love it. It is just fantastic stuff. It will fail over between regions. It will fail over specific VIPs if you're running multiple front-end load balancers. It's probably the easiest way to get basic GSLB running for any of your services. You can do BGP in Anycast, but then you are probably Dynect, or your Google, or your Facebook. If you're running in the cloud, you're probably not doing this unless there's a way you can do this in the cloud, but I doubt it. You can do cookies, you can do user config. Getting your users to a different data center can either be done with code or with cookies or things like this. It's really easy to just go buy a service from Dynect. I'm not pushing that product. I really like it. For performance and cost, obviously we're going to talk about instance sizing. You need to run the smallest instance that you can while still being at the right level of performance. This is where all the monitoring comes in. Don't even bother with 32-bit. It costs the same. It's easier if you're running Java applications that want to use a lot of memory. It's easier if you just start out with 64-bit. Two C1 mediums cost about the same as one M1 large in EC2. If you've got a CPU-based workload that doesn't require a lot of memory, this basically doubles your capacity for the same cost. Smaller for us, an instance size that's smaller than an M1 extra large won't run Cassandra well. That's just us, and we're still tuning and working with Cassandra on our own applications. But from what we've done, from what we've tested, swapping in and out instances, anything smaller than this does not work well for us. And you can mess with with Java, you can mess with your garbage collection and your memory settings to then either constrain the amount of memory that they use and still cache and deal with your memory effectively. And therefore, if you can constrain the memory, you can run a smaller instance size. So we do a lot of these tests quite frequently. We test out the instance sizing probably on a weekly or a monthly basis. And this is what we did, I believe, in Europe. We were running C1 mediums, and we don't see as much traffic in Europe as so many of our other regions. And we decided to try an M1 small. And I think you can spot it pretty readily. Load average, again, isn't really all that interesting as a metric. In fact, it's a bogus metric. But as a 10,000-foot view, or as sort of something to just even tell you to dig in a little bit more, load average actually worked pretty well in this case. And what was interesting was that we didn't see much of a performance decrease on this particular server. It was still serving the same rate as all of the other instances. It was still serving them at maybe just a slightly slower response time. But because it was holding on to those connections for a little bit longer, we knew that as traffic ramped up, this server would fall over faster than the other ones because it was holding onto these connections for longer periods of time. And that's where just the basics of CPU monitoring, load monitoring, and request rate and latency told us, well, we can't go this small. This is as small as we can go with the C1 mediums. So with reserved instances, you trade your upfront costs for your longer term operating costs. It hurts a little bit upfront because you're still paying maybe $1,000 for, I don't know, I think for a 1-year contract with a C1 medium, you're paying about $1,000 upfront. But you get a fraction of the operating costs thereafter, depending on which size or which utilization type you use. Reserved instances are fantastic for the bottom, for the trough of your traffic graph. If you know you always will have a baseline minimum amount of traffic, you would never shut down more servers than what it takes to serve that up. So why are you spending more money on on-demand instances than you need to and swap them out as reserved instances? Sometimes when you are either about to take on a new client or you know that you're about to take on a lot more traffic, you can offset this front-end cost, this painful upfront cost, by including some of the costs, honestly, in the client deals. This can be a very reasonable thing to do, especially for a early stage company that's taking on clients. This actually, it works well. It's more of a contractual technique than a technical technique, but it's useful. For minimum or medium and low utilization reserved instances, when you spin down the instance, you are no longer paying the hourly rate. So even if you need a baseline of coverage for your bottom of your traffic usage, you can still buy medium utilization or low utilization reserved instances on the opportunities where you actually do drop maybe a little bit below. Or maybe your cost analysis will show you that it's still cheaper to buy these types of reserved instances instead of going on demand. Vimeo has a deck out somewhere at SlideShare that talks how basically they game the whole entire marketplace of reserved instances, spot instances, and on-demand instances, where they in turn effectively save something like 50% over the cost of using all on-demand instances. And we're seeing something about similar. We're saving about, at the moment, we're saving about 40% ourselves by switching to reserved instances. You have to do a little bit of your own calculations, your own cost analysis to figure out what, if it would be worth it, and if it would be even worth it to, say, reserve instances for 3 years. It also gets more interesting now that Amazon has come up with their own marketplace where you can give back or sell back your reserved instances, especially high utilization ones, to other people, other companies, and then you don't have to pay, you wouldn't have to pay the hourly usage even if it's turned off, which is pretty cool. All right, so some more technical stuff, finally. Deploys. All right, there are several ways to do deploys. There are basically two types that are sort of popular these days, especially with EC2, is one is sort of a rolling deploy where you roll through each server and take it offline, deploy new code, bring it up, and that takes a, however amount of time based on however many servers you're deploying to and how many you can take down at a go. And the other way is to bake all of your applications into an image or basically spin up an entire copy of your infrastructure and then flip a switch that then directs all of your traffic over to the new infrastructure. The latter terrifies me. Even with all of the testing, all of the Q&A that we do, or QA that we do, I would be terrified to flip over all of my traffic all at once on the off chance that there's some new feature was introduced, some new bug was introduced, and suddenly all of the traffic is problematic. So we do the rolling deploys. If you're deploying code in this fashion and you're taking your application down, you're doing it wrong. There's absolutely no reason that you need to take your app down and to do a deploy. And one of the easiest things to do is to add health checks. So you have, let's say in the case of an HTTP-based service, you have an endpoint in your service that either your front-end load, that both your front-end load balancer hits to determine if your server or your instance is alive, and an endpoint that you can also use to control and tell that server when it is or is not healthy. So you can take a server down right before it's deploying. You can turn traffic on and off to that server. And you can even hook in, you can make it an intelligent health check that's tied into, are all my database connections up? Do I have I pre-warmed my own my local in-memory cache? Have I done everything that I need to do on startup? And once all that stuff is taken care of, then I'll report back healthy. There's also another way you can do this for non-HTTP based or non-load balanced services, so like smart clients. And there's a link there at the bottom that talks about smart clients versus load balancing versus scaling needs. You can put all of the intelligence, all of the load balancing smarts into your client. Suddenly your clients are basically, they include their own load balancer in them or their own load balancing logic. So when you take down a service, your clients detect the error, they back off, they do retries, and then they do fuzzing when they want it, when the service comes back up, so that not all of your clients knock your service offline immediately. So basically, you can take these services down without even thinking about it, without cooling down or draining traffic. You just shut them down, and all the clients behave appropriately. And then finally, for deploys, tag deploy units. So you're pushing out WAR files, you're pushing out tarballs, you're pushing out what have you. You can tag those deploy units so that on the machine itself, it's keeping a certain amount of history of that application having been deployed. So if you know that you need to do a fast rollback, even through the same deploy mechanism, you can identify which tagged deploy unit you need to roll back to, go and talk to every single machine and pull itself back to its previous version. And I've got some examples of these. These are the health checks that we use. Again, testing with curl, it's an HTTP service, and all it does is report its current state. It gives a 200 class response if it's okay, and it gives a 500 class response if it's unhealthy. And you can see here in the middle bit there that we can actually tell the service to put itself into maintenance mode. So while this is happening, as the load balancer comes in and checks this health check endpoint every 2 seconds, every 5 seconds, every 1 second, it'll come in and start getting a 500 class error to start, and then we'll start taking that server offline, start draining it. But what it also does is it lets the remaining connections that are on that server continue to drain off. So it's not like you're unplugging the machine at once. Everything that's currently on that system or on that service gets drained off slowly and cautiously, and nobody knows the difference. It won't receive any new connections. So you, during a deploy, you tell a particular service or a particular instance that it's in maintenance mode, wait a few seconds for the connections to drain off. Then it's no longer receiving any connectivity. You can safely shut it off, keep it off for however long you want, deploy new code, bring it back up, and roll on to the next one. So in this case here, we've checked the health of the service, put it in maintenance mode, check it again, it continues to report unhealthy. We check it again, and then in this case, this would be like a scenario where you're turning traffic on and off to a service. So imagine if you've got a real-time logging configuration on this service. You can turn the traffic off, wait for it to drain, set your logging config up to debug or for whatever certain module that you want to increase the logging on. Turn the traffic back on, watch your logs, do a quick log sample, or whatever you want to do with this new setting that you've applied. Then turn it back off, set it back to its normal production settings, and then turn it back on again. Really, really handy stuff. It seems like it's a really simple thing, but the more you can make use of it, even if you are doing these entire forklift deploys and upgrades of an entire fleet of instances all at once, having something like this allows you to do a lot of production and runtime debugging in an environment that is not testing. And this is what in HA proxy, this is what that health check configuration looks like, talking to those servers. So pretty simply, it just checks that URL. If it gets a 404 or anything basically other than a 200, it takes that machine out of rotation. All right, tag deploy units. This, I believe, if I remember correctly, is just a straight up PHP application. And the only thing that's interesting here is that each one of those directories that's got a timestamp on it is a different version of the application, about a week apart. And then a symlink that points to the current version. I think this is something that's pretty common in the Ruby world as well. What's neat about this for even your straight flat HTML applications through Apache or through PHP is that by deploying to a new directory and then flipping a symlink, you have, and then by specifying in your Apache config the path to your web root being the symlink and not one of the actual directories. As soon as a request comes in, Apache checks to see where it's going to open a file. It opens the file. It basically dereferences the symlink, and then opens whatever inodes it needs to open that file. When you change the symlink, everybody who's currently on the site and currently has, and which Apache processes have those files open, will continue to serve those out. Those users will be drained. And as new connections come in with new processes coming up, reopening file handles, they will get the new application. So it's almost like deploying without necessarily even having a health check. But it reasonably, gracefully moves traffic over from the previous version of your service to the new version. So for performance in SLA, multi-availability zone is really neat, but multi-region, I think, is the best. If you can get your application working in a multi-region config, you've won. I mean, it's one of the harder problems to solve. But if you can get it baked into the app from the beginning, it's perfect. It makes life and traffic and moving traffic around and serving your users, or running your service closest to your users, all the better. You have to make some decisions up front. Obviously, you don't want a lot of traffic going back and forth between the regions. And even particularly with Amazon, your internal nodes in, say, West cannot speak directly to your nodes in East, unless you're setting up software VPNs and that kind of stuff. But if you can deal with the application and tell it that, or basically design it so that you don't ever rely on internal communications between clusters or between servers. Suddenly, it makes each region being its own standalone system all the better. And to do this, you need to know what you want to keep local and what you do want to occasionally go remote for. So particularly as reads versus writes. For some people, reads are more expensive, writes are more expensive. You just have to sort of figure that out. In our case, for writing statistics, we write all of our statistics locally in each region and do roll-ups and aggregation on the fly on the read. And for sending out configuration updates, we push those out in real time through a message passing service, which I'll get to in just a second. Like I said, you can use effective aggregation or distribution as needed, whether or not it's on the read or on the write or both. So let's see, this is a little abrupt here. But one of the services that we use, and I believe we are considering open sourcing this, it's actually really, really simple stuff. But it's basically a Node.js application that we call Hiveway. What it receives on the front end is a post of a payload, in our case JSON, and what it does is it just passes that out to another system or another Hiveway. All it is amplifying the connection between one or two services. So messages come into a local Hiveway. That local Hiveway is aware of all the other regions that it needs to talk to. It then sends out that message to all the remote nodes, and then those remote nodes or those remote Hiveways either put things on a queue, talk to services directly, flush caches, do all sorts of things. So what we're doing is we're basically funneling and proxying cross-region traffic and updates. It turned out to be really, really handy stuff. What we've also done is for our tag servers, when they start up, they have to go and talk across regions to go find what their current config for a current client should be. Originally, we had these requests going across for every server, so that on a deploy or on a restart, every server would have to refetch the same configuration per every number of servers. A lot of repeated traffic, a lot of repeated effort. So what we did is we changed our Hiveway structure so that not only was it passing messages out, but it was also receiving and caching those messages. So now instead of in each region, each of our tag servers requests the Hiveway locally, it more than likely has that configuration cached. If it doesn't, it goes and fetches it from some other site, pulls it back in, and then on the next tag serve that gets deployed, that gets restarted, suddenly it has 80% or 90% of its cached configs, and no traffic goes across regions. For our stats, this is something where I was talking about writes and reads versus local and remote. When we do the writes, for every request that comes into one of our tag servers, we write out a metric, a one-to-one ratio of every request gets one written metric. That metric then goes to a stats receiver that then writes out to a data store, and in this case, this is MongoDB. That receiver writes the raw metric, but then also writes the 1 hour aggregate, the 30-minute aggregate, and the 30-second aggregate. So we do the roll-up, we roll up the data in real time so that we don't have to process it and get large data sets to read it and to read in those larger chunks. So we keep the writes local, but then we do the retrieval across the regions, and we still do aggregation there. So a request for our stats metrics comes into a retriever in region 1. It then, again, like the Hiveways, it knows about all of the other remote sites, and it then takes in the same input request that it receives and passes it on to the remote sites, gets the data back, and then collates it, summarizes it, aggregates it, and then sends it back on to the caller. And that's how we do our biggest multi-region connectivity bits. I've been speaking really fast because I'm a lot earlier than I thought I would be. So we have lots of time for questions if anybody's interested. If you want more tech questions or want more technology about what we do, some of my colleagues did a presentation in Chicago about a month ago. That's the URL there. If you want to hear more about the company, we do a lot of technology postings on our blog about our design methodology, our culture, how we go about building our application from an engineering standpoint. That's on our blog. And you can just come say hello, talk to me. I love talking about this stuff, although I talk about it too fast sometimes. Anyway, thanks.
And do we have any questions? Questions?
Hi, Tom.
Hey, Joe.
I'm kind of scared of you.
Thanks for the talk. Could you talk about the robustness of the messaging and the durability of messaging that you have in Hiveway?
It's honestly, it's not terribly durable. It's meant to be. We put in our own exponential backoff that on the case that a tag serve starting up requests a config from a remote Hiveway. If either that Hiveway is too loaded, doesn't have a config, or for whatever reason it gets a bad message, the tag serve will back off because it can't do anything without that config, and it will then re-request it. Usually in that time frame, either the Hiveway can go retrieve it on its behalf, or it's already received a cached update from somewhere else. It was just sort of part of the design that we knew it was acceptable to not have that kind of durability. Anyone?
So for your monitoring and your messaging, how do you keep that redundant enough? Like, I mean, you expect nodes to go away every so often. Do they automatically spin up again, or do you have redundancy?
We have a whole one bit that I didn't talk about. We have a whole underlying service manifest system that keeps track of the nodes, when they spin up, what services are running on them, what ports are running on those services. And if they go down, then they get removed from the manifest. It's a little bit lazy. It's a little bit, it's not real time, but that's how we keep track of things going up and down. And then our monitoring ties into, pretty much everything ties back into the manifest system, which is also distributed like all the other applications. The monitoring ties into the manifest system, and when it notices a new node of a certain type, it then automatically starts creating graphs and polling metrics and things for it. Does that answer your question? Close enough? Okay. All right. Thanks.
Thank you. All right, so.